essentially all my research was on the effect of ceramic frit on the load resistance of rectangular glass lights. All of them are heat treated just due to the process of it. So I'm going to do a little bit of background first on essentially how the glass is made and processed and what implication that has on the strength. So as a precursor to the research, what was being seen is my professor and another colleague of mine were seeing that there was some glass frit and spandrel applications that were fracturing due to thermal stress. There were a couple of different projects where they were seeing that there was thermal stress breakage. It was always in the spandrel light. And, you know, after you see so many of these similar fractures, you start thinking, okay, there must be a root cause or a similar mechanical flaw somewhere in there. And so digging a little more into the research, you see that the European codes actually currently reduce the strength of heat treated glass once you go through and apply a frit. And there are some differences between European codes and US codes that make us being able to do this a little more difficult. But essentially what happens is in European codes, they're designing their glass using a maximum stress method. So they assume that the glass always fractures at wherever the maximum stress in the glass is. Once you go through and you apply frit, they add, I believe it's a 30% reduction to the strength of glass. In North America, we design using ASTM E1300 generally. There are some things that fall outside of the scope of that standard, but for the most part, glass and facades is for wind load resistance at least is designed with E1300. And at this moment in time, there isn't anything in the standard that accounts for a load resistance reduction when frit's present, even though we know that there is some impact on the load resistance from this frit. And one of the main differences between the two standards is that in the US, we design using a probability of failure method. So it's acknowledging that there are inherently critical flaws on the surface of the glass that can cause it to fail below the location of, or below whatever the maximum principal stress in the glass is at the time. Once the glass comes off the line and starts being processed and washed and things, you start gathering these little these little flaws called Griffith flaws on the surface of the glass, and they become locations for concentrated stress essentially. So in order to help prevent the potential to under design or over design, we essentially go through and we just design using a failure prediction model. So everything I present in here, I'm going to focus really on that designing to the probability of failure of 8 in 1,000. And you'll kind of see where I'm going from there. But really, where the conversation has gone is we've said that, okay, well, all of the fractures that are occurring are due to thermal stress that we've seen, not wind load. So maybe we shouldn't put it in our wind load standard or in our standard to design wind loads, right? But there is also not currently an ASTM standard in place to design for thermal stress in glass design. And so that kind of leaves this gap of, well, we know it's happening, but it's not affecting this one standard. And we don't really have a place to tell people otherwise. So we'll just kind of wait until we have something. And that's really what caused the article that you saw and you discussed in that last podcast episode, right? So if you'll move forward, okay. So just a little background in how this works. Essentially, we have our float process to create the glass. So we have our raw materials go into a melting furnace at 1500 C. Essentially, all the bubbles are pulled out. This molten glass gets poured onto a molten tin bath and is floated over that to give it the flat properties that you see. And it is pulled to be at the whatever thickness the glass is being designed to be. Afterwards, it comes out of the tin bath, goes into the annealing furnace to help relieve any residual stress that may in the surface may be within the glass, and then it is cut and packed. So that's just a general layout of how glass is made. Where this comes into play is in the next slide, where we see how frit is applied. So after the glass is cut and packaged, it's sent to a fabricator. At the fabricator's location, they apply a frit. So they could apply it through a couple different methods: roller coating, screen printing, digital print. Kate probably knows there's others that I maybe didn't mention, but generally the frit is applied onto the surface of the glass. And the frit has these glass particles or ceramic glass particles in it that after it's applied, you put it into your tempering furnace, and it's heated to a near melting temperature, not quite melting, but enough that whenever it's rapidly cooled, the ceramic frit is now fused onto the surface of the glass. So they're now one cohesive element, and it can't be scratched off. So what this does is, and this is something that whether it's fritted or not, when it goes through the tempering oven, you essentially are creating this residual compressive surface stress in the glass, and that's what determines whether it's heat strengthened or fully tempered. In this top picture, you'll see this is a piece of glass that doesn't have any frit or enamel on it, and you have this symmetric residual stress within the glass, where you have tension in the center and you have this layer of compression along the surface, and that's really what's giving it the additional strength that you're looking for. So whenever you go through and you add that ceramic frit, you see within the glass you actually have an asymmetric surface stress at the glass surface, at least, because theoretically your maximum residual compressive surface stress should be occurring on the surface of the enamel. And so when you go through, you design heat strengthened, theoretically has a load resistance of 2 times annealed glass, and fully tempered should have a load resistance 4 times annealed glass. So this is just a general background on where we're starting. If you move forward, Kate. So what I've done is I've kind of broken out, I've just taken 2 phases of what my research was to give an idea of what this load resistance reduction looks like. So initially we did some small sample 4-point bend tests, and we use this just as an observation of, does ceramic frit impact load resistance? Does it matter which surface it's on? How much? Kind of just as a gauge of, is there an actual change in mechanical failure whenever you apply ceramic frit? And then the second, our uniform pressure test, more what you would see in terms of 4-side simply supported piece of glass. And in this, we went through and checked varying percentage coverage, and we're able to see where the location of failure was with regard to the frit coverage on the glass. So we'll go over both of those. Next slide. So we'll just start with the 4-point bend test. In these, they were really small samples, nothing, about yay big, handheld. But we did 4-point bend test. So essentially your maximum stress would be the entire area between your top 2 loading pins. So that way we knew it was always fracturing at a location of maximum stress. So we went through, we tested heat strengthened and fully tempered lights. In these, we had our uncoated controls, and we tested with the frit in tension and the frit in compression to see if there was any difference with regards to where the location of the frit was. So next slide. Yeah, so here we see our just a general layout of our load at failure, or our 3-second equivalent failure load, and our probability of breakage. So we're going to focus down towards the bottom, but as looking at a general rule, you see that your control and your when Frit is in compression have fairly similar failure distributions, at least in terms of the coefficient of variance. You see a similar trend, and sorry, I forgot what I was saying. You see a similar trend, but once the Frit was in tension, suddenly the coefficient of variance significantly reduced. Now you're seeing, okay, well, whatever is breaking this, it's the same mechanical sense of mechanical failure every time. It's happening very sudden. It's happening at around the same stress or the same load every time. And so we, if you look at your, we'll say like mean failure load, what we started seeing was that fully tempered glass is actually performing less than at a load resistance less than that of heat strengthened, and heat strengthened was performing less than our annealed samples that we ended up testing later on. And so it's pretty significant whenever it comes to designing for load resistance. So if we move forward to the next slide, you'll see focus down at a 8 in 1,000. And yeah, I mean, it's a lot closer in this whenever you get down to a probability of failure of 8 in 1,000, but we're still seeing 40% decrease in heat strengthened glass and a 20% decrease at heat strengthened glass once you start putting that fritted side in tension. And some of the tests that we did in this, actually, we saw that the glass was fracturing at a stress lower than the recorded residual stress that we measured, which means that potentially the residual compressive stress on the fritted side isn't as high as it would be on the unfritted side. So if you, next slide. This is just a quick layout of what those percent reductions look like. We can move forward. Yeah, so whenever we realized that the glass was fracturing at stresses lower than the measured RCSS, we did use a wet etch process to remove the frit and try to measure what those residual compressive surface stresses were, and we found them to be significantly lower than that that are actually defined as heat strengthened or fully tempered by ASTM. So next slide. So now I'm just going to move forward to our uniform pressure test. These are, you could go ahead and move forward. These are just a 4-side simply supported tests. Essentially what we did was we had these large scale tests. We put them in this frame and used a vacuum to create a uniform pressure on the surface of the glass. In this case, we were testing everything with the frit and tension because we knew that was where, that was essentially where the issue was. And so, next slide. What we did was we tested our control, and then we had a varying percent coverages with this frit, and it was all a gray frit. So we did a 40, 50, 60% coverage, and then a full coverage. Move forward, and you can see here's what the example of the patterns look like. So we had our dots, our lines, and essentially the reverse of the dots. So we just had these holes. So again, here's just another, you see the distribution of them. Once we applied the frit onto the glass, all of those essentially not sample and everything else had frit on it, the coefficient of variation significantly reduced. So we know it's the same, probably the same reason for mechanical failure that we're seeing in our previous tests. And again, at this mean level, there's not really a clear correlation with regard to what your percent coverage is. So it wasn't like 40% reduced it this amount, 50% reduced it a little more, 60% a little bit more. It wasn't, there was no clear answer on that or solution to show how that worked. But what we saw was there was significant load resistance reduction in general. So next slide. And here's just at probability of failure of 8 in 1,000. So you can see what that looks like with regard to E1300 design. So Yeah, so what we saw was, I mean, we have essentially a percent reduction, a load resistance reduction ranging anywhere from 16 to 38%. Interesting that note on sample 2 and 4, they're fairly close in what their percent reduction was, and really their patterns were exactly just the inverse of each other, right? So it may have something to do with like the layout of the pattern versus the stripes that you know, followed a different layout. So I don't really have an answer for that necessarily, but essentially what we're seeing is that you're still getting fairly significant reduction. So next slide. Really, like, what does that mean? Well, really, when we're designing, I think the last thing as engineers any of us want is to go through and make an uninformed decision on some of this design, right? And a lot of firms are actually going through, and at least until E1300 adopts something, just either using some sort of percent reduction or just automatically fully tempering anything that has frit on it, so they at least get heat strength and load resistance. But the next slide has a little more design implications on it. Oh, I forgot about this. Yeah, so one of the other interesting things we saw really is that the fracture origins always occurred under the location of frit in all of the samples that we saw, whether it be the dots, the stripes, or the holes. You could see here on the left picture, the fracture origin occurs right in the middle of that circle of that dot. And in this, where that red arrow is, what you see is there's actually ceramic frit that is embedded within the fracture origin of the glass, which kind of leads to believe that it's potentially the frit being embedded into flaws that may be on the surface of the glass, and causing some tension on there that's essentially reducing that, what is supposed to be the compressive surface stress that's built in from your tempering process. In the next slide, there's another picture that's a little clearer. In this right picture, you can very clearly see where the frit is and where that location of fracture was. So it's always directly underneath an area where there was frit on it. And I'm on my last slide now. So, no, I'm not. So really, some of the possible causes is there's potentially flaws on the glass surface during application. So that's why we're finding the frit in the fracture origins. And another thing may be that you're getting more heat loss on the enamel side during the tempering process. So potentially by adjusting the tempering process, you can go through and create a lower or create a more even residual compressive surface stress, but that's a lot more work needs to be done on that in order to see if that's even possible or a plausible thing to do. So really, next slide, Kate. Where this impacts design and leads into some of the discussions that you had on your podcast previously is a lot of the breaks are happening due to thermal stress. And so what things have an impact on thermal stress resistance? Well, one of the recommendations that I'm not sure who was, someone on the team said was, okay, well then I'll just design with a thicker light. If you're getting this load reduction, you could design with a thicker piece of glass, give it a little more strength. But whenever you're designing to resist thermal stress, increasing the thickness of the glass doesn't improve that stress resistance. Really, what's increasing the thermal stress resistance is your residual compressive surface stress that occurs from the tempering process. So if you are designing with frit and you have something that's heat strengthened spec, probably want to move forward and just make that a fully tempered light. Impact when you're designing for wind load, well, by adding a percent reduction, it doesn't necessarily mean that you're going to increase the thickness of the glass. A lot of times you could add a 20%, 30% strength reduction, and it's not going to change what thickness you're selecting, because most of the time when you're designing for wind load, the glass selection tends to be governed by deflection and not by load resistance. So most of the time you won't even see a change in it with regard to your wind load resistance. Where you might see some of this change is now you're seeing an introduction of first surface bird-friendly solutions. Legislation is introducing a lot of bird-friendly glass, and so as you start seeing maybe more first surface ceramic frits come to light, that's when you might want to start taking this load reduction into consideration for wind load resistance. And so my final note that I would say is, if you're using ceramic frit enamels, I would highly recommend just fully tempering the glass to prevent breakage. I know that leads to other associated risks, but otherwise you're really leaving yourself open to potential thermal fracture risk. So now that was kind of the end of my test results, so I'll hand it over to Kate, and she could go over.
Great, thanks, Kayla. So I will present about a coating option that does not weaken glass, and then we can get to a discussion and a Q&A over everything that was presented today. So thanks, Kayla, for sharing your expertise and research on ceramic frit's weakening effect on glass. And the role that my company, ICD, played in this research is we actually participated in a white paper that was released probably about 5 years ago now, alongside Texas Tech University, Chris Perry, glass consultant, Dow, and a facade engineering firm called Morrison Hirschfield, to determine whether silicone coatings, which is an alternative to frit that is applied after the heat treatment of glass, also has the same weakening effect. So I'll be showing you the 4-point bending test results of silicone, as well as ball drop testing, which is not related to thermal stress, but it also gives a hard number on the impact resistance of glass. So I always like to start with just a brief definition of what spandrel glass is, because in the podcast, I know maybe there was some questioning about why it's used. And so first, I like to just show that spandrel glass should always be near opaque, used in non-vision areas, interior surfaces not suitable as a finished wall, and it must be cavity backed. So if it doesn't have a uniform backing in place that completely eliminates light transmission, otherwise you're going to see application textures, pinholes, and just general non-uniformity as seen in these photos. So once installed correctly, it will appear 100% opaque. It can be used for its functionality, so it's commonly designed to conceal structural and mechanical elements from exterior view, such as floor slabs, vents, electrical wiring, mechanical systems. And from a design perspective, it can be used for aesthetics, so decorative applications to have, bright, fun colors. Material mimicking, sometimes architects and designers will send in physical samples of, for example, the framing that's going to be used around the glazing, so the spandrel glass can match that. Retrofit or rescan applications, or to have a contrast on the facade. Or harmonizing, which is one of the more common design goals, is where you want the entire facade to have that nice seamless blended look, and spandrel glass can achieve that as well. So now I'll just show some examples of how thermal stress breakage occurs in spandrel glass applications. So thermal stress occurs because of solar gain, even though there are reflective and low-E coatings that are sometimes used for the spandrel cavity, often used for that visual continuity. Solar heat energy can still get through between the glass and the spandrel insulation, which heats that cavity up. Then the center of glass heat loss is somewhat restricted. So if you do have a reflective or low-E coating, along with the composition of an insulated glass unit, it reduces heat loss to the exterior. And then the insulation, the cavity backing behind the spandrel glass, reduces the possibility of heat loss to the interior. So therefore, that cavity gets very hot. The solar gain, coupled with the restricted heat loss, allows the center of glass portion of the spandrel glazing to become very warm. And at the same time, the surrounding framework chills the perimeter of the glazing, so the warmer center of glass area expands relative to the colder perimeter, creating tensile stress. And it's when the stress exceeds the strength of the glass when breakage can occur. So here is a visual of the center of glass area, which gets hot from solar gain, surrounded by a perimeter area that is cooled by heat loss through the framing, which can result in a crack forming. Now, annealed glass, which is just referring to glass that has not been through the heat treatment process, takes a temperature differential of about 91 degrees Fahrenheit to induce enough tensile stress to cause breakage. So when you see a single crack like here on the left, the temperature is likely within that range. But when the cracks begin to branch out like this, that tells us that the temperature difference might be much higher with more stress in the glass, with heat-treated glass. So here's just a real life example of a building that had glass that was broken due to thermal stress. So there was an insulated glass unit that was heat treated for the spandrel with a low solar gain low E coating on surface number 2 and an insulated sheet metal backpan behind the glazing unit. And the inboard pane of glass is cracked with a ceramic Frit opacifier applied to surface number 4. And looking closer, we can see the top of that crack and how it branches out at the spacer with temporary support installed to hold the glass in place. And zooming in, you can see the fan, and the branching of the crack is actually starting out above the spacer. So not right at the edge, but within the depth of the spacer and perimeter sealants. So taking that unit out and flipping it around, now we are looking at surface number 4, which is referring to the interior facing surface with an applied ceramic Frit. The crack is on top and moves downward toward where it fans out to the center of glass area, and the crack progresses toward the edge of the glass, fanning outward in that direction as well. And this tells us that the crack origin is somewhere in this region between the two fans, which is significant because cracks in annealed glass typically begin right at the edge of the glass. And in this case, the crack is clearly beginning inward away from the edge. So basically what I'm doing here is just showing visual characteristics of glass that has been broken due to thermal stress. So now we're looking at the face of the crack on one half, and there are components that tell us this is the origin. First, there's a semicircular shape referred to as the mirror. Outside of the mirror, there's a fine pebbled area known as mist, and following that's a jagged radiating pattern known as hackle. So collectively, this tells us that the crack began up at the top on surface 4 where the Frit is applied and radiated downward to the left and to the right. And at the bottom, we see a wide black band. This is the perimeter sealant and spacer, showing that the geometric center of the mirror is within the depth of the spacer, not at the edge, but inboard from the edge. So naturally, one of the questions that arises when discussing thermal stress is how can I find solutions on how to prevent breakage occurrence, right? And so a common question that arises is, can ventilation be used to remove heat from the spandrel cavity? And with rain screen wall design for brick, the cavity is typically drained from behind the brick to the exterior to remove moisture that may penetrate. And vent holes are included at the top of the brick panels to provide opportunity for air to flow through the cavity and help dry out that moisture. So Morrison Hershfield Engineering firm carried out a test program to determine the effects of ventilating spandrel. So here is a simple test assembly. There's 2 frames of 3 panels. The 3 on the left are just monolithic single pane, and the 3 on the right are insulated. And here the glass is clear, so you can see the insulation and wiring that was used to calculate temperatures from within the assembly, and that will also be used as a control against the opacified unit results. So the first approach is to fully seal the perimeter of the glass, typically occurring in a 4-sided structurally glazed application. The second condition has only drain openings at the bottom, which is the traditional approach for draining spandrel. All spandrel glass applications should have some sort of water mitigation system in place to eliminate moisture buildup. And the third has vent holes at the top and drain holes in the bottom to test if you can get the same air circulation benefits that are known to occur in brick masonry, and see if this method can remove heat that can build up in the cavity. So now analyzing the results of that testing, first we're looking at the graphs of the 3 conditions with clear glazing. The orange line is the sealed 4SSG, the blue line is the drained, and the green is the vented. And with monolithic glass, venting seems to have somewhat of a small beneficial effect, but all 3 are well below that danger zone of, this is in Celsius, so 35 degrees Celsius, where thermal stress breakage could happen. So spandrel ventilation does not make a difference. And with insulated units, there's not much of a difference between the three options, and we're just starting to reach the level of danger of thermal stress breakage. Now comparing against the opacified results, looking at the condition for monolithic, the temperatures increase but are still below that 35-degree critical range. But for IGU, you can see they now start to reach out of that range. So there's a risk that can be dealt with by heat strengthening the glass, but adding a ceramic frit can take away some of that benefit, as we saw in Kayla's presentation. And I'll be showing a coating alternative in the next few slides.